welcome you all for our next GATE lecture video series. In this video, we are going to discuss about operating systems deadlock topic. So myself is Krishnaveni, Assistant Professor, Department of Information Technology, SA Engineering College. So first we are going to discuss about the definition of deadlock. So what is deadlock? Deadlock is a situation in a multi-processing system where two or more processes are unable to continue their execution because there are no available resources for execution. That is the situation arises when we are going to multi-processing system. For example, if two people are using same resources, if we are taking two persons, one person is holding a pen and another one person is waiting for the same pen, this same person having the situation, this is deadlock. When the particular person complete his task with the pen, after that only the requesting person can get the access of that pen. So this is the situation of deadlock arise. Same as when we are going to the multi-processing system, process A hold some resources that should be requested by process B, then the process B still under the waiting at the time when process B getting the resource of process A. So necessary conditions for deadlock. There are 4 conditions for deadlock. First one, mutual exclusion. Second one, hold and wait. Third one, no preemption. The fourth one, circular wait. Now we can discuss one by one. So first one, mutual exclusion. From this name itself we can identify here the resources are not shareable. Involved in deadlock must be non-shareable. This is only one process can be used the resource at a time. We cannot be access the resource when the resource is under the process. This is mutual exclusion. Example, a printer can only be used by one process at a time. This is mutual exclusion. Second, hold and wait. Hold and wait, from name itself we can understand if a process is holding at least one resource while waiting for another resource held by the other process. This is hold and wait. For example, if process P1 holds resource A and wait for resource B which is held by process P2. If process P1 already having the resource A but it is waiting for resource B, that should be held in the another process P2. Okay. Next, preemption, no preemption. This means resources cannot be forcibly taken away from the process holding them. They must be released voluntarily. We cannot be forcibly take the process resources. This is under process. So example, if process P1 holds resource A and does not release it, other processes cannot be preempted to avoid a deadlock. If process P1 holds a resource A, another process are in requesting stage means they have to be wait till process P1 release the resource A. Okay, this is no preemption. Then circular wait. It is like hold and wait, but hold and wait is only between two processes, but here we can move with the more number of processes, so it is in continuous cyclic process. This is called a circular wait. So a set of processes exist such that each process is waiting for a resource held by the next process in the chain, forming a circular dependency. Yes, if process 1 waits for resource B, that should be held by P2. Same, P2 waits for resource C, that should be held by another one process P3, and P3 waits for resource A. Then resource A should be held by P1. Here P1, P2, P3. They are in circular cyclic motion. Each one should be dependent on each other process resources. So they both three set of processes are under waiting for resources. This is called circular wait. This is all the necessary conditions for deadlock. So first one, mutual exclusion. Second one, hold and wait. Third one, no preemption. Fourth one, circular wait. This is all the reason for deadlock arise in a process of operating system. So next, deadlock prevention technique. Yeah, we know about what is the condition for deadlock creation. Then how we can prevent from this deadlock. So to avoid the deadlock, one or more of the Hoffman conditions, these four conditions must be removed. Yes, these four conditions must be removed, then only the system is called as deadlock free system. There are several techniques for prevention. So first one, eliminating mutual exclusion. So what is mutual exclusion? Mutual exclusion means the process is not shareable. Yes, not shareable means explanation. Not all resources need to be exclusion. Some resources can be shared among multiple processes. We cannot design all the processes all the resources are under exclusion. This is separate for each and every process, not like that. You should give some resources under shareable one. Okay, example, you make files in read-only option. If we make read-only option means more number of persons can access the file. The file is also under in safe state. Okay, read-only files can be shared between processes without leading any deadlock. More number of processes can access the resource. Eliminating mutual exclusion, then eliminating hold and wait. Hold and wait means one process depend upon another one process because of resource utilization of other process. A process must request all required resources at once. At the one time itself, the particular process can request the resource. Then only other process cannot hold the requested resource, because already the requested process can understand, yes, this particular resource should be holded by another one process. A process must request all required resources at once. This prevents process for holding resources while waiting for others. Example, a process must request both CPU and printer at the same time instead of requesting one and waiting for the other. Yeah, this is eliminating hold and wait. If I am a process P1, I want to utilize both the CPU and printer means from initial itself I want to request all these two resources at the one time. Okay. Next, eliminating no preemption. Explanation, resources can be preempted from a process if necessary. If necessary means the resource should be preempted. So example, if a process holds resource A but needs resource B, resource A can be taken away and reassigned if a deadlock situation arises. So already we discussed preemption means resource cannot be forcibly taken away. If a process can voluntarily release the resource, till that the requested process can be waited. This is preemption. So in this, eliminating preemption means if a process holds resource A but it is waiting for another one resource P means process P1 voluntarily release resource A and start utilizing the another one resource B. This is the situation for avoid deadlock in no preemption. Next, eliminating circular wait, P1, P2, P3, whatever which n number of process, but each and every process under dependency of resources. This is circular wait. So preventing circular chain of waiting process by imposing linear ordering of resource types. So we can give a numbering for each and every resources. Then as a process can follow the linear order of requestation. Example, resource can be numbered. Yes, R1, R2, R3, it may be numbered, and a process must always request resources in increase increasing order. Yes, first process P1 wants to use resource R1, then it's moved to R2, then it's moved to R3. So this is the linear order of requesting resources. So the process can access it. If process P2 wants to access resource R3 means it can analyze whether the R3 is accessed by any other process. If it is not means it can directly requesting the resource R3. So the situation of circular wait, this is circular dependency, should be avoided while using the linear ordering of resource type. This is all deadlock prevention technique. So conditions for deadlock: mutual exclusion, hold and wait, no preemption, and circular wait. So how we can avoid, how we can get a prevention from deadlock means we can use some alternative method for avoiding these conditions in deadlock situations of processes. Okay, the next we are moving for deadlock avoidance. Deadlock avoidance ensure this is the system never enters an unsafe state. This is, we must give the assurance my process is under in safe state. So we have to state safe and unsafe state. What is safe state? A state is safe if there exists a sequence of processes such that each process can get its requested resources, execute and then release the resource. If I am having a set of process, if one process P1, it can get all the requested resources, it can get, it can execute, it can utilize all the resources, and after utilizing it can release the resource. Then the particular process P1 is set as process P1 is in safe state. Okay, this is called safe state. Then unsafe state would lead to deadlock. Here the particular process under in deadlock, that means the requested resource is not utilized by a particular process as no such a sequence exists. So deadlock avoidance means mainly we are giving two important keywords, safe state and unsafe state. Safe state means there is no deadlock. If a particular process is in safe means the process can get the requested resource, execute and release the resource. Then it's safe. Unsafe means it leads to a deadlock. It cannot get the requested resource. So here using the Banger's algorithm for deadlock avoidance. So here we are considering one example, considering a system with 5 processes starting from P0 to P4, okay, and their resources of types A, B and C. 3 resources A, B and C. Resource type A has 10 instances, B has 5 instances and type C has 7 instances. Okay, suppose at time T0 following snapshot of the system has been taken. Time T0 there is a situations of the processes. Here we are having 3 important things: allocation, maximum and available. So we have 5 processes and 3 resources. Maximum allocation and available. This is the snapshot at the time of T0. Now we move with some questions. First question, what will be the content of the need matrix? Need matrix is based on our maximum and allocation of resources. So need is a 2-dimensional array, is fully depend upon the maximum and allocation. So formula is need of I comma j is equal to maximum of I comma j minus allocation of I comma j. So from our previous table, allocation and maximum, so we want to calculate each and every process need from maximum minus allocation. First P0 maximum is 753. So 753 minus 010. So we can get 5743. 743. This is the calculations for need matrix. Need means how much resources we more for process the system. Okay. So this is the calculation for need matrix. Next, how we can calculate whether the processes are under in safe state or unsafe state. If the system in a safe state, if yes, then what is the safe sequence? We are following the sequence. So apply the, here we are going for the safety algorithm on the given system. Safety algorithm, we are using work and allocation. Step 1 of safety algorithm, we are considering here M and N. M is resources. Here we have 3 resources, A, B and C. So M is equal to 3 and N is the number of processes. So here based on our problem, our example, we have 5 processes, P0, P1, P2, P3 and P4. 3 resources A, B and C. So M is equal to 3 and N is equal to number of process 5. Okay. So M is equal to 3 and N is equal to 5. In first step, we are considering work is equal to allocation. How much resources allocated for a particular process? For P0, how much allocation? P1, how much allocation? P2, how much allocation? This is available. This is called work. So work is equal to 332. This is available 332. This is first initialized as work. Okay. So work is equal to 333 and also we can initialize finish. Finish is 5. This is P0, P1, P2, P3, P4. Initially all should be declared as false. So finish is equal to 5 phase. It's all declared as false. Then second step, for I is equal to 0, first iteration, I is equal to 0 means process P0. Process P0, we are taking need. Need means P0 need 743. So condition must be need less than or equal to work. Initial our work of P0 330, condition must be satisfied when need less than or equal to work. So first check whether a finish of 0 false and we need to check need less than or equal to work. Our need is 743. It is greater than 332. So P0 must be under in unsafe state. So we are moving to the next iteration. This is for I is equal to 1. Process P1. We are taking need under process P1 1, 2, 2. So now 1, 2, 2 check with work 3, 3, 2. Condition is satisfied. This is need less than work. So finish of 1. P1 must kept in same sequence. So we have to change this finish of 1 as true. So next step we can see finish of 1 is changed as true because condition is satisfied. This is need less than work. So here true means that work should be changed as not only allocation. Already we have some work plus allocation. Okay, we change the formula of work as work plus allocation. So already we are initializing work as 332. So here allocation of 1 is 200. This is process P1 allocation 200. That should be added here. Work plus allocation 332 plus 200. So now our new work value is 532 and also finish of 1 is true. So next step we are moving to the second iteration. This is process 2. Process 2 need value is 0600. So that value should be compared with work. So So 600 to 532 condition is false. So process P2 must wait. Then we are moving to the next iteration. I is equal to 3. This is process 3. Process 3 need value is 0, 1, 1. So 0, 1, 1 is less than work, condition true. So process 3 must be kept in safe state. That means finish of 3 should be changed as true. Okay. So we have to get the new work value. Already we have a work value was 532 plus allocation of 3. This is process 3's allocation. Check with the table. Process 3 allocation 211. So 211 is coming here. So both should be added and we can get a new work value. This is 743. This 743. So we are moving for the next iteration. This is process 4. Process 4's need is 431. This should be compared with the new work value. 431 is less than 743. This is P4 must be in safe state. So we have to change our finish 4 as true. Next step. So finish 4 is changed as true. Then it is true means we have to update our work value. This is work is equal to already having a work value plus process 4 allocation value. So 743 plus 002 we can get a new work value as 745. Okay, so now we have go to this next iteration. I is equal to 0 because we are finished 4. Again is a circular motion until all the values should get true. This is all the process must be in safe state. We are getting the sequence. So first is sequence P1, then P3, then P4. Now again we are moving to the iteration of 0. So process 0, this is process 1's need value 743. 743 is less than 745. So our process P0 must be in same sequence. So we are changing finish of 0 as true in next step. So finish of 0 is true and our work value should be changed. So work plus allocation of 0. Allocation 0 value is 01 plus. So both are added and we can get a new updated work value 755. So we are moving to the next iteration. This is I2 because already I1 is true. Next I2. Because it is false value, we are concentrating on process P2. So getting the value of need 2, this is 600, this is less than 755, condition true. So our P2 must be in same sequence. So we are updating finish. This is finish value of 2 as true. So finally we can get all the value as true and also sequences P1, first P1, P3, P4, then P0 and P2. This is our same sequence. Everything we can update. This is the same sequences of process. So this is the deadlock avoidance. Once again I give a small recap. So first for this deadlock avoidance we are using the safer algorithm under Banz's algorithms. First we are concentrating some terms: maximum, allocation, available and need. This is given in this snapshot. So process need we can calculate from maximum allocated resource minus allocation. So we can get the need value from this table. And also we are moving for the safe state. First we can get the initialize the value of m and n. M is the number of resources, n is the number of processes, and we are using work initially is equal to available. If we are moving to the iterations, each and every iteration we can compare need with work. If need is less than work means we have to update the process finish value. This is whether the process is safe. This is the iteration value. So circularly we are check whether the need less than work, then the condition true means we can get the sequences of process safe state. Okay, so for this problem we can get the sequence in the P1, P3, P4, P0 and P2. This is the safe sequences of given processes. The next topic, deadlock detection and recovery. How we can detect and recover from the deadlock. In some system, it's better to detect deadlock and recovery from it rather than prevent it from the occurring in the first place. Rather we are going for prevention. Initially we have to detect it whether it is occurred or not when we are moving with the process and resources. First concept, wait for graphs. A wait for graph is a directed graph where processes are nodes and the edges represent the fact that one process is waiting for another process to release the resources. So it's not a circular wait, it's not a hold and wait, nothing. Here we are designed as a graph. This is directed graph, while processes are designed as the graph node. What is the concept behind it? One process is waiting for another resource. Not all the processes are going for same resource. They should be held in another process. Not like this. We are creating the graph like this. One process is waiting for another process to release the resources. A cycle in this graph indicates the presence of deadlock. Whether the cycle is created, whether P1 is waiting for R1, but the R1 is held by another one process. This is cycle formed means it indicates the deadlock. So deadlock detection algorithm. The algorithm repeatedly check for cycles in the system resource allocation graph or wait for graph. We are using some techniques for detection whether the resource allocation having the deadlock or not. If the cycle is found in the graph, the system detects a deadlock. Then how we can recover from a deadlock? Once deadlock is detected, the system can recover by either killing one or more process. Yes, if resource R3 is requested by P1, P2 or P3 at same time means killing one or more process. This is P2 and P3 should be diverted to other one or removed from the requestation. Directly P1 can assist R3. So killing one or more process involved in the deadlock. Second one, rolling back process to a safe state. Yeah, already we discussed in safe algorithm. So we are moving the same algorithm, rolling back the process. If it is true or false, checking whether the need should be less than work. There's a process checking, everything is handled here for deadlock recovery. So okay, this topic, deadlock detection and recovery. So before going for prevention, first we have to detect it. For detect it, we are using wait for graphs or system allocation graph. Here one process can allocate for one resource. Sometimes it may create deadlock because of the cycles of requestation. So that's a situation we have to avoid it using recovery methodology. First one, killing one or more process, rolling back process. So next we move to gate questions on deadlock. So following questions, before moving to the following questions, we have to concentrate important one. This is two types. One is minimum number of units that ensure no deadlock. If process and resources, everything is having, we have to calculate minimum number of requestation. So for formula is minimum number of units of resource are that ensure no deadlock means one more than maximum number of units of resource are that ensure deadlock. This is we have to add one more units of resource. This is minimum number of units. Maximum means we have to minus 1 from minimum number of processes. Here processes, here resources. So minimum and maximum, two problems we are going to discuss in coming section. So minimum number of units asked means we have to add one more in resources. If it is asking maximum number of units means we have to minus 1 from the minimum number of processes. So the first question is, a system is having 3 user process, each requiring 2 units of resource R. So we have 3 processes, P1, P2, P3, each one requesting 2 units of resource R. The minimum, here question underline minimum number of units of R, such that no deadlock will occur. Minimum. So already I am told you 2 types of question, minimum and maximum. Minimum means we have to add 1 to the units of resource R. Okay. So first we have to calculate. A system is having 3 users. Same question. We have 3 resources, P1, P2, P3. So 3 process and each process requiring 2 units. 2 units means in worst case the number of units that each process holds is equal to 1 less than its maximum demand. So here maximum demand is 2 units. So we have to 1 less it. Okay. So 1 less than its maximum demand. Our maximum demand is 2. So process P1 holds 1 unit. This is 2 minus 1, 1. Process P2 holds 1 unit. Process P3 holds 1 unit. In worst case, the number of units that each process holds is equal to 1 less than its maximum demand. Our maximum demand 2, so 2 minus 1, 1. So each process holds 1 means we can avoid the deadlock. If another one system is requesting 1 means we can provide another one. This is 2 resources. 1 is allocated to P1. If P4 is requesting same time means we can allocate this another one to P4. So formula we are moving. Maximum number of units of resource R that create deadlock is, you should add all these units. 1 plus 1 plus 1 is equal to 3. So here we are asking minimum number of units of resource R that ensure no deadlock. So units of resource R that ensure no deadlock means 1 more. This is 3 plus 1, we can get 4. So 4 is our solution. So we are moving to the next question. A system is having 10 user process, each requiring 3 units. So 10 process, each asking 3. So how we can calculate here? P1 till P10. So each asking 3 means in worst case 1 less than resource. So P1 occupies 2 units till P10 2 units should be allocated. So the minimum number of units of resource to avoid deadlock means first you should add 2 plus 2 plus 2 plus till 10. So answer is 20 and minimum number means 20 plus 1 we can get 21. So totally 21 minimum number of units of R we have means there is no deadlock will occur. Okay. So next we are moving to third question, same pattern. A system is having 3 user process P1, P2 and P3 where P1 requires 2 units of resource R, P2 requires 3 units of resource R, P3 requires 4 units of resource R. The minimum number of units of R that ensure no deadlock. So P1 requires 2 units. So for calculation we are taking 1 less units. So 2 minus 1, 1. P2 requires 3 units. So 3 minus 1, 2. P3 requires 4 units. So 4 minus 1, 3. So now we are adding these all. 1 plus 2 plus 3, 6. So minimum number means 6 plus 1, 7. So our answer is 7 for this question. If I am having 7 number of units of R, this is resource that ensure no deadlock. Okay. The next question. A system is having 3 user process P1, P2, P3. P1 requires 21, P2 31, P3 41. Then minimum. Same problem like this. So how we can find out the answer? P1. If I am taking P1 is for calculation 21. So I am here taking 20. P2 31. I am taking 30. P3 41. I am taking 40. So first add these all. 20 plus 30 plus 40. So 90. Then minimum means we can add another one. So answer is 91. If I am having 91 minimum number of units of resource, then my system is under in safe state. There is no deadlock. This 4 problem related to minimum number. Now we are going to the maximum. If there are 6 units of resource are in the system, 6 means P1, P2, P3, P4, P5 and P6. Each process in the system requires 2 units. Each process occupies 2 units. Then how many processes can be present at the maximum? How many processes? Here discuss about no resources process. So that no deadlock will occur. So in worst case, the number of units that each process hold. So same problem here. You can take like this. P1 till P6. Each process requires 2 units means 2 minus 1, 1. So each process occupies 1 units of resource. So totally we have 1 plus 1 plus 1 plus 1 till 6 process. We are getting answer as 6. So this is asked about maximum. So maximum means minus 1. So 6 minus 1 we can get 5. If I am having maximum of 5 process, then my system is not having the deadlock. It is in safe state. Okay. So next problem, if there are 100 units of resource are in the system, each process in the system requires 5 units. I am totally having the 10 processes, but each process requires 5 units. 5 units means process P1 requires 5 units, process P2, P3, P1 requires 5 means it should be minus 1, so 4. P2, 4. Like this, if I am going process P25, it's also 4. Totally I am having 100 units of requestation. So total number of process 25. Here I am having total number of process 25. So 25 minus 1, 24. So if I am having 24 maximum number of process means the deadlock should be avoided. Here not concentrate on resources, only process. If P1 occupies 4, P2 occupies 4, at the time of 25th process, my all requested 100 unit resources should be utilized. Process P25 means 100 units should be completed. So total number of process 25 minus 1 we can get the maximum number of processes. So the last one, if there are 100 units of resource are in the system and each process in the system, at the time of P25 4 units occupied, so 25 minus 1, 24. So answer is 24. The next, a system has 6 tap drives with n processes competing for them. So the process needs 3 taps. So P1, here P1 occupies, totally we have 6 process, each process need 3 tapes. So P1, 2, P2, 2, P3, 2. 6 tapes, we are using totally 3 processes. So 3 minus 1 is equal to 2, 2 is the answer. 6 tapes drives in n process. So first process means we are having 3 resources, 3 minus 1, 2, P2, 2, P3, 2. Totally we can get 6 at the number of process P. 3. So 3 minus 1 is equal to 2. The answer is 2. If I am having 2 number of process, there maximum number of process, then there is no deadlock. We are discuss about the definition of deadlock and simple examples about deadlock. What are the necessary conditions for deadlock? This is mutual exclusion, circular wait, preemption, hold and wait. This is all the maximum conditions for deadlock. Then next, safer algorithm using whether my process is safe or unsafe. This is all discussed, and deadlock detection, deadlock prevention. Finally, we are discussing about minimum number of resources and maximum number of process problem. Hope you all understand the concept, and next video we will move to the next topic. Thanks for all your timing. Thank you.